So, we start today important topic, that is cyclostationary processes. It is a special kind of random process which is not fully stationary, but it does exhibit some sort of stationarity and occurs frequently in many applications, especially in digital communications. Also called periodically stationary processes. Actually, these processes are such that their statistics that vary periodically over a constant time period. Okay. That is, if I talk of a cyclostationary process which is strict sense cyclostationary, that is, if x t is SS stands for strict sense cyclostationary, this would imply that if you take the probability distribution of f, that is, let me make it capital. By the way, what does this mean? Though we have already done it, but still there is nothing wrong in just restating what you already know. This is the joint probability distribution function of any random process x t. That is, it is the joint probability of, that is, by definition, what is this? Probability of what? X at t 1 lying less than equal to x 1, x at t 2 lying less than equal to x 2 dot 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 x at t n lying less than equal to capital X n. This is the joint probability. This is called the probability distribution. Okay, and this number n, there is a number of sampling points you are choosing, that is purely up to you. You can take it from 0 to up to infinity. Now, if the process is stationary, we know if the process is stationary, strict sense stationary, not cyclostationary, but strict sense stationary, that time we have seen that this joint distribution for any n that we choose, that does not depend on this exact values of t 1, t 2 to t n. Rather, if all of them are given a constant shift or constant delay, that is, if t 1 is replaced by say t 1 plus c, t 2 is replaced by t 2 plus c, the same c, dot 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 t n is replaced by the t n plus c. In other words, if the time origin is shifted by an amount c, then still you get the same distribution function. That is, the statistics does not depend on the exact location of the time. Okay. There is the relative positions of t 1, t 2 to t n, that is what is important. Okay. Then that is strict sense stationary. In this case, if it is cyclostationary, then this would imply that this is equal to, just give me a minute. This would imply that this is equal to if instead of t 1 I give a constant shift which is an integral multiple of a basic time period capital T. So, t 1 plus either t or 2 t or 3 t like that, say m t, m is an integer. Then again t 2 plus m t, m is an integer, dot dot dot. Okay. Just a minute. Then dot 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 t n plus m t, if they are same. So, that is the joint distribution function, and also therefore density, whatever be its value at this time points t 1, t 2 up to t n, you will get the same thing if you move over, either move forward or backward by capital T for each of the indices, or move 2 t or 3 t or minus t, minus 2 t, minus 3 like that. Or in other words, if the time origin is given a shift either to the right or to the left by integral multiple of capital T, then and only then it will repeat. So, it is not fully stationary. It is not that these two distributions are same for any shift that you give, but the shift is only m into t. It is not c, and it is not true for any c, but that constant c, that is the shift of the time origin, that is only some integral multiple of a basic period t. Okay. Then this is called a strict sense cyclostationary process, or also periodically stationary process. Obviously, this means that suppose you take, suppose this is your x t, whatever you take at 0 t equal to 0, then at t at 2 t dot dot dot, okay. You take its samples at m t, okay. Now, if you just take them, what does that mean? That if you take just this sequence that is x 0, then the first sample, second sample is x 1, then x, that is x t, then x 2 t, that 0 8 1 2 like that. Then you can easily see that this sequence becomes actually a stationary sequence, okay, strict sense stationary sequence. Obviously, because if you want to take the joint density here, if you take say few samples, if you take up to the few samples, so 0 up to n, okay, nth sample x n t, and you take the joint density, that is basically the joint density here of the samples. Okay. Now, if you give a shift there by any amount, the shift is actually in integral multiples of t, that is if you shift. So, from 0 you get to 1, or from 1 you get to 2, or from 2 you get to 3, basically in time axis you are getting shifted by either t or 2 t or 3 t like that. Okay. So, from the cyclostationarity you should get the same joint distribution function, right. So, if you sample it at t, 2 t, 3 t and all that, then the sequence that you get, that is strict sense stationary. Okay. This must be obvious, because what is this after all? I mean, what is the joint distribution? This is nothing but x 1, x 2 dot 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 x n at time 0 t 2 t dot 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 say n t. You start at x 0 say, okay. And then if you sample, if you give a shift to this sequence, so 0th sample moves to first and like that, okay. That means basically you are giving a time shift by capital T, but from cyclostationary of the original process you should get back the same probability distribution function, okay. So, that means there is some relation between before coming to that, this means that if you really take, if you form a discrete process m t, okay, say some sequence x m as m t, okay, then this sequence becomes strictly stationary, okay. This sequence becomes strictly stationary, because here suppose you take, as I was telling you, you take the joint density, joint distribution x tilde 0, x tilde 1 dot 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 x tilde say anything you can take, say k samples, okay. Instead, if you give a shift here, instead you take x tilde, this instead of 0 you jump by 1, so 1 x tilde 2 dot 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 say x tilde k plus 1, these two are same. That because comes from the cyclostationarity of the original analog process, because this samples corresponds to which time indices 0 t up to k t, and here instead of t, instead of 0 you are taking, you are advancing by capital T, instead of t you are advancing by 2 t, advancing by t, so we are making it 2t, and likewise. Okay. So, the sample version, when you are sampling at a rate capital T, that becomes a strict set stationary process. Okay. In this context, some relation are very much useful. One is this, that suppose x t is given to be SS strict sets cyclostationary. Okay. And instead of x t, you suppose shift it by theta. So, you get another process, we call it x bar t, okay, where theta is random, theta random variable uniform, that is uniformly distributed over 0 to t, which t, the same t, over which this is cyclostationary. X t is cyclostationary and the basic period there is capital T, and you are shifting it by a theta, where theta is uniformly distributed over 0 to t. So, you get another random process x tilde t or x bar t. Then our claim x bar t is strict sets stationary. Strict stationary, and if you take f bar stands for the distribution function, joint distribution function for this new process x bar t. If you take that is equal to, this is our claim, 1 by t integral 0 to t original distribution function x n and t 1 minus maybe alpha dot 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 t n minus alpha d alpha. Okay. So, we prove this first. So, first we consider this, what is the meaning of this distribution function. When I said f bar x 1 dot 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 x n comma t 1 dot 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 t n, what does it mean? It means it is equivalent to probability of event A, where A is what? This new process x bar t 1 less than equal to x 1 dot 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 x bar t 2 less than equal to x 2 x n. This is the probability, take it. Now, we have to show that this process x bar t is strict set stationary. Okay. If it is strict set stationary, that means instead of t 1, if I give a constant shift c, so is t 1 plus c, then t 2 plus c dot 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 t n plus c. Okay. And then this distribution becomes equivalent to probability of event A, where event A is simply this, that at time t 1 plus c, x bar within bracket t 1 plus c less than equal to x 1 dot 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 x bar t n plus c again less than equal to x n. Okay. This is the event. Okay. So, instead of t 1, t 2 up to t n, I am just giving a constant shift or constant delay or advancement, whatever, to those time points by the same. So, I am just shifting all of them by a constant amount c. I have to show that this probability distribution is independent of c, and then only it will be proved that this x bar t is a strict sense stationary process. Okay, that is, whatever be the shift you give to the time origin on the time axis, the probability distribution, the joint probability distribution does not change. So, we consider this event A, which is this, that is the process at value at time point t 1 plus c is value taking less than equal to x 1 comma dot dot dot, its value again at time point t n plus c taking values up less than equal to x n, the joint, this joint event, this means, so probability of this event is actually this distribution. Now, one thing, x bar t 1 plus c. So, within that actually what is x bar t 1 plus c after all? It is x t 1 plus c minus theta by definition of x bar, and therefore, in this process x bar there are two random components. One is coming from the original process x bar t. So, every time you observe you get some data, but again that is delayed by another variable theta which is also random. So, there are two random forces, two random phenomena that are occurring simultaneously. One is from this process x t, another the delaying variable theta. Okay. So, that means P A is nothing but P A comma theta d theta. This is a joint density of the event A and theta taking some value, okay, and theta is taking values over the range 0 to t, and this is P A theta, as we know, is nothing but P A by theta into P theta, and P theta is what? Theta is given to be uniform from 0 to t. That means, within the interval 0 to t, its probability density is constant, and that is equal to 1 by t. So, that the area is 1. So, that 1 by t is P theta, 1 by t comes out of the integral, and this 0 to t d theta. Okay. This means that implies what? But what is P A by theta? We know the event. This is simply joint probability of what? For a given theta, what is the value that the process at time t 1 plus c takes values less than or equal to x 1 dot dot dot, its time t n plus c, that is x bar within bracket t n plus c less than or equal to x n. Okay. But we know this thing, that x bar t is x t minus theta, and in this context theta is constant, that is given a particular theta. So, theta is no longer random. Okay. So, that means when I say that x bar t 1 plus c less than or equal to x 1, this is equivalent to saying x less than or equal to x 1 dot 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 x t n plus c minus theta less than or equal to x n. Okay. That is using our notation. This is nothing but probability distribution of the original process x 1 dot 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 x n integral. What are the time points? t 1 plus c minus theta dot 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 t n plus c minus theta. So, you have to substitute this P A by theta here in this integral and get that probability. That will be the joint distribution of the delayed process x bar t, and that will show that that is independent of this constant c. Okay. So, if you really remember this, you are going to substitute for P A by theta by this expression, multiply by theta, integrate from 0 to t and multiply by 1 by t. Okay. That means, if I erase this part, that means our starting point was this. This was our starting point, sorry, T 1 plus C, T n plus C. This is equal to, this you have seen, P a by theta d theta integral 0 to t multiplied by 1 by t. So, we simply substitute the above expression f actually from this only, using your intuition, you can make this inference that look, theta is the integral variable and you are integrating over one period, because this distribution is periodic. If theta jumps over by an, if theta is replaced by theta plus a capital T, that is theta increases by jumps by a factor capital T, you should get back the same probability distribution function simply because of the cyclostationarity. So, this distribution is actually periodic in theta. Okay, because if theta is replaced by theta plus capital T, you would get the same thing, because theta plus capital T means this net thing, net time index for all the points, they get, I mean they get subtracted, I mean capital T gets subtracted, right, that is minus 1 times T get added. So, from cyclostationarity you would get the same probability distribution function. So, that means this is in the periodic in theta and you are integrating this over one period. So, what value you should get, that should not depend on your T 1 plus C. Okay. That is, it should not depend on your this constant C. Anyway, this comes from intuition, we can easily prove it, we can easily get what this expression would be. Okay. This is actually simple mathematics now. Suppose theta minus c, I say alpha equal to theta minus c. Okay. That means this integral will be what? When theta equal to 0, alpha is minus c. So, from minus c to t minus c. Okay. That means this integral will become equal to 1 by t d alpha, right. And now, maybe I can erase this part. Then this integral, one part is from 0 to t minus c, if you want you can call it 0 plus, the same thing comes here, d alpha, and again 1 by t, in other case it is from minus c to 0 minus, the same thing, d alpha. Let us consider this second integral. In the second integral, if suppose alpha is replaced by alpha prime plus t, or sorry, suppose I bring a variable alpha prime, which is alpha plus t, okay, alpha plus t. Then what happens? When alpha is minus c, this becomes t minus c, and when alpha is 0, this becomes t. Okay. So, integral limits change to, now integral limits will be changed to, this will become t minus c, this is alpha prime, and this becomes t. Okay. And within this we have got this probability distribution function, but alpha to be replaced by alpha prime minus t. So, you have got instead of t 1 minus alpha, now we have got t 1 minus alpha prime minus t, t n minus alpha prime minus t. So, everywhere I am giving a constant shift by capital T, and from the cyclostationarity of the original process, you should get back the same distribution function as given by this, because see, going forward or backward by capital T or twice t or 3 t would not change anything, right. So, you would get back the same thing, and then you replace again alpha prime by alpha. Why use two different variables? So, two integrals can be brought together. So, 0 to t minus c and t minus to t. So, you basically would get, finally, you will get this thing 1 by t 0 to t f So, you see this entire thing is independent of that original shift parameter c. Okay, original shift parameter c. Okay. So, this is the expression we wrote that time. So, this proves that this process x bar t is a strict and stationary process. Okay. Actually, this is often important, because in communication sometimes, I mean, this baseband waveform that you transmit, that basically you choose a pulse, and then this pulse is multiplied by the symbols, and you get a pulse train, each pulse modulated by a particular symbol, and that since symbols are coming randomly, this entire thing becomes and continuous value random process, that will become cyclostationary, but then often that process gets delayed while reaching the receiver, and the delay variable theta, okay, or phase shift, whatever, that is often found to be uniform. As a result, the delayed process turns out to be strictly stationary. Okay. That is why this context is, this example is important. Then, if you have strict sense stationary, obviously you have also wide sense cyclostationary. Okay. Also called WS cyclostationary. Here, this would imply that if you take the mean at a particular time, say x t, it is no longer like in the case of stationary process, you have seen when you come down to WSS, that time it is no longer the joint distribution that we consider, we just take the mean and the correlation. Here also we take the mean, and if you call this mean t, in the case of stationary process, this become independent of t, but if it is cyclostationary, that is in the case of stationary process, if you take any indices t 1, t 2, t 3, you should get the same mean. Here it is not so, you would get the same mean, provided instead of t, you either go forward or backward by capital T or twice t or 3 t, like that. That is, this is equal to where m is an integer, that is m is from z. Okay, this is number 1, and in the case of correlation, that is say r t plus tau and t. There is two indices, the two time points I am taking, one is at t plus tau and the t. This is same as, say if you consider real valued process, this is same as, or in the case of complex value, this is this. Okay. If it is cyclostationary, then this correlation, even though it is a function of, in the case of strict sense stationary, what happened? These two time indices t 1 and t 2, that is t plus tau and t, they didn't matter. What mattered was the separation tau. In the case of cyclostationary process, this is not so for all t, but for specific values of t, that is either small t or small t is replaced by t plus capital T here and here, or t plus 2 t, that time this gap, the separation which is always tau, that should come into play. Okay. That is, it should become a function of tau, not at all t, but at the time points that are separated by integral multiples of capital T. Capital T is the basic period over which it is cyclostationary. That is, if t is replaced by t plus m into t, m being an integer, plus tau and t plus m t, only then these two correlation values will be same. That is not, it is not that this correlation function becomes a function of only the gap or lag, that is tau, for any t, but this indeed becomes a function of tau only at certain choices of t, that is either t or t plus m t, t plus capital T, t plus 2 t, t plus, at these 2 points the gap is again tau between these 2 time points, okay, time indices, but it is not true for any t. So, this is the definition of White's cyclostationarity, and obviously you can see that if the process is given to a strict sense stationary, it is also cyclostationary, White's cyclostationary, or not vice versa. Obviously, I mean, like in the case of you will take the expectation, right. That means you if the process is given to be say strictly SS cyclostationary, then we know this density is same as T 1 plus any m t. What does this density means? That is probability that x t 1 or T 1 plus m t takes values within this range between x 1, I am talking of density now, not distribution, d x 1. Okay. And what is eta t? Eta t, you simply multiply x 1 by this, eta t 1 say, that will give you eta t 1. Similarly, if you want to find out eta at T 1 plus m t, instead of T 1 you make it T 1 plus m t, but since it is strict sense cyclostationary, okay, the two densities are same and you get the same result. So, if it is strict sense cyclostationary, it is also White's cyclostationary, at least for the mean we have seen. Same you can see for the correlation also, that is what is R t plus tau, sorry, considering real valued case. Okay. That is how will you calculate it? You multiply these two by the joint density. Okay. What is the joint density? That is P x 1 x 2 at t plus tau and t, meaning the joint probability that at x at t plus tau, x t plus tau lies between x 1 and x 1 plus d x 1, and x t lies between x 2 and x 2 plus d x 2. You multiply these two functions x 1 and you multiply these by x 1 x 2, integrate over x 1 x 2 over the entire range, then you will get this. If t is replaced by t plus m t here, you would get the same integral, is because from the strict sense stationarity the two distributions or densities will be same. Okay. So, that follows obviously immediately. So, we do not spend more time on it. So, similarly, in this case also we can show that suppose x c is White's sense and you generate x bar t as where theta is a random variable uniform over 0 to t. Then our claim is x bar t will be WSS, okay, with its mean mu will be 1 by t and correlation tau will be 1 by t integral 0 to t or t plus tau comma t dt. Okay, we prove this. Okay. Now, how do we find out this quantity? For that matter, we define this density p bar x t the same as p bar a, where a is this event x bar t at this time point t takes values within this zone. Okay. At time t, this process x bar t takes value within this zone. Okay. In that case, it is simply x p bar a dx. But as I told you earlier, p bar a is nothing but p bar a by theta into p theta, okay, and p theta is 1 by capital T. P bar a is what we have seen earlier, is p bar a comma theta d theta over 0 to t, okay, over the entire range of theta. But p bar a comma theta we have seen earlier is nothing but p bar a by theta into p theta, that is 1 by capital T, because p theta that is uniformly distributed over 0 to t, and that 1 by t goes outside, and d theta. Okay. And here theta is fixed. So, what you get here? If you replace p bar a by this expression and interchange the two integrals, what you get is 1 by t 0 to t, okay, 1 by t 0 to t, then this integral, this d theta comes here, this integral minus infinity to infinity x p bar a by theta dx. And what is this? Theta is fixed here. So, that means x bar t taking value x bar t, which is also equal to, we know, x t minus theta, and theta is fixed. So, p bar a by theta is same as the probability of x taking value x t minus theta taking value, that is the process x t at time point t minus theta taking value between x to x plus dx. So, this will give rise to expected value of the process at t minus theta. I repeat, theta is fixed, p bar a by theta means for a given theta. So, once theta is fixed, look at this event a, x bar t is same as x t minus theta. So, this probability of a subject to fixed theta is what? The probability of x t minus theta, this random variable taking values between capital X to x plus dx, that multiplied by x integrated, that will give rise to the expected value of this random variable x of t minus theta, which is eta of t minus theta, right. And then it is very simple. you have this integral one by t sorry t minus theta. Once again, this eta t, because of the cyclostationarity, we know this is periodic over a period capital T. So, eta t, or similarly, if theta is replaced by theta plus 2 theta plus capital T or theta minus capital T, you would get the same thing because of the cyclostationarity, because the net argument gets shifted either by plus or minus capital T or plus or minus 2t and so on and so forth, or you are integrating this over an entire period of theta. So, this eta, if you plot it as a function of argument, then basically you are integrating one period, integrating this function eta over its one period and averaging. So, that should not depend on whether I put t here or minus theta here. I can call it, I can give it any variable eta of say alpha, d alpha, okay, 0 to capital T 1 by t. You can always put like this. This comes physically, and again if you still want to verify, sorry, if you still want to verify this, it is not very difficult. You can call this alpha. Okay. So, that means when theta is 0, alpha is t, and when theta is capital T is t minus t, d theta becomes minus d alpha. So, the two integral limits get interchanged. So, essentially you get 1 by t, as I told you, t minus 0. So, it was t, lower limit was small t, upper limit was small t minus capital T, but that gets interchanged. So, t minus capital T and then t alpha d alpha, and again this you break in this form. We have already done it from 0 plus to t, the same the integral, and another integral is again 1 by t from t minus t to 0 minus, same integral. Okay. And rest is very simple. You can, as before, you bring in alpha prime as alpha plus t. So, when alpha is t minus capital T, alpha prime is t, and when alpha is 0, alpha prime is capital T, and then the two integrals you just come under one umbrella, you get that result. Okay. That means, we prove this part, sorry, we have proved this part that I called it alpha, now again I am calling it t, it does not matter, it is an integration variable. In the same manner, R bar we wanted to prove that is R bar is basically a function of tau alone, because it is fixed and stationary. Okay. Actually, this should be, I am sorry, I should remove this dependence on t now, because this entire thing is just a constant, you see. Okay. If you replace t by, if you just substitute t by, I mean, this is just a formula, this is just a result which is constant, and that is eta bar. Okay. Similarly, my claim is that this delayed process is a fixed and stationary process. I have not yet proved it, I have proved it with the mean. For the correlation, that means I have to show that the correlation becomes a function of tau alone. Okay. This will show, but for that, so I am just writing as a function of tau, but I have not yet proved it. I keep that in mind. We will show, we will get its value. This actually is what? This is a general expression. And what is that? As before, E of x bar I am assuming real, otherwise you put a star here. And how to carry out this integral? You have to find out, that is, this should be, this bring this joint density P x 1 x 2 t plus tau and t x 1 x 2 dx 1 dx 2. Okay. But this joint density I can write as a conditional density, that is, if I that is, this is subject to theta multiplied by p theta integral 1 by cap, okay, and p theta is integral 0 to t, and p theta, that is, sorry, this part I will write as p, if we call this event a by theta into 1 by t 0 to t theta, this part. Okay. And then what happens? You take the integral with respect to theta outside, inside you have got x 1 x 2 multiplied by this joint density. What is the meaning of joint density? That is x bar t plus tau taking value between x 1 to x 1 plus dx 1 and x bar t taking values between x 2 and x 2 plus dx 2. But x bar t plus tau for a fixed theta, now x bar theta is fixed here, for a x bar t plus tau is same as x t plus tau minus theta, and x bar t is same as x t minus theta. Theta is fixed here, mind you, because this is now conditional density. Okay. So, if you carry out the integral from the previous logic, it is then nothing but, this will give nothing but sorry that outer integral was there 0 to t, and inside you will have original r at t plus tau minus theta comma t minus theta d theta. Okay. So, I write in a neater way here. So, what I get, maybe I move to the next page, what I get is this r bar tau, we have not yet proved that it is indeed a function of tau alone. So, still I am writing knowing beforehand. So, actually it is, as I told you, r bar t plus tau comma t, this we have shown, it is nothing but this integral original r t plus tau minus theta comma t minus theta d theta, and then this remaining part is very simple. If you call theta minus tau to be, if you call theta minus tau to be theta minus tau to be some variable, say tau 1 or alpha. Okay, then this integral becomes what? Same thing I am doing again. In the next class, I will take just an example of cyclostationary process, because then we will get a practical feeling. Okay. When theta is 0, alpha is minus tau. So, from minus tau to t minus tau. Okay. And this becomes r of t minus alpha just a minute. Sorry, it should be instead of tau, I should take this theta minus t to be alpha. Okay. So, it is when theta is 0, this is t minus t, and when theta is capital T, it is t minus t, and then r or maybe I can make it still better, still more convenient for you. Forget about this. Suppose I call t minus theta, which is common, as some variable, say alpha. Okay. That means this becomes 1 by t. When theta is 0, this is t. When theta is capital T, this is t minus t, or and then d theta becomes minus d alpha. So, this integral limits will be changed, a minus will come. So, this becomes this, and this remains because d theta is minus d alpha. So, minus comes and the two integral limits are interchanged. So, minus sign goes, and this is your alpha plus tau comma alpha. From this again it is obvious, okay, because the entire thing is periodic over alpha over a period capital T. Still, if you are not convinced, you can break the integral into two halves. One is from 0 to t, that is 0 plus to t, same thing. Another is from t minus t to 0 minus, same thing, okay, dt. Concentrate on this integral. Second one, here again bring this variable alpha prime is alpha plus t, same way. So, d alpha and d alpha prime are same. When sorry, these integrals are with respect to alphas. D alpha so, d alpha and d alpha prime are same, and when alpha becomes t minus capital T, alpha prime becomes t. When alpha becomes 0, alpha prime becomes capital T, and the two integrals can be brought under the same one, and you get the result. That is a function of tau alone. What you get is r, you can call it alpha, you can bring back t again, say does not matter, because that is an integration variable t dt. So, you can call it alpha as well instead of t, 0 to t 1 by t. This is your r tau. So, this process is strictly in the stricture stationary. Okay. These are some applications in communication. We will take one example. Okay. The example of pulse amplitude modulation waveform PAM. So, that will give a practical feeling, and you will understand why we spend some time on it. After that, we will move to systems, that is processing of random processes by some linear systems or nonlinear systems, time invariant systems, and all that. And that will take us to finally spectral analysis, power spectral density and things like that. Okay. So, that is all for today. Thank you very much. Okay. So, today we discuss systems with random processes input. Suppose x t is a random process. That means, you conduct experiment, and with every time you have an experiment, you know you observe one waveform, right. So, maybe one particular waveform we denote as before like this, where SI denotes the ith outcome. Okay. So, in the ith outcome you get a waveform as a function of time. So, this is represented by x t comma S I. So, it is actually a function of time. S I just denotes the fact, S I just stands for the fact that it is related to the ith outcome, a particular waveform. Now, suppose we have some kind of rule, we develop or we have some kind of rule by which given particular waveform we generate another waveform by a rule, some waveform we call it y, and obviously that waveform also is associated with the ith outcome of the experiment. Okay. So, that means we can write it as y t s I. For example, you can for example 1 comma t 2. Now, here we have got r x x t 1 comma t 2 is a function of actually r x x t 1 minus t 2, t 1 minus t 2 equal to say tau. Okay, so, it is a function of tau. So, here I know it is 1 minute. Here if you take this derivative del r x x t 1 minus t 2, okay, t 1 minus t 2 is tau, you differentiate with respect to t 2 first and t 1 first. I leave it as an exercise to you, you can easily verify these two things, r x x tau r x prime tau, you can easily verify will be r x x tau first order derivative and r x prime tau will be second order derivative. Okay. So, that is all for today. Thank you very much.